So the next presentation is about application of machine learning techniques predict intermittent earth fault in medium voltage distribution networks. And the presenters are Mazaher Karimi and Meysam. I don't know how to pronounce it.
Pashaei. Meysam Pashaei.
Okay, thank you. From the University of Vasa, Finland. So can you share now the scene?
Great. So first of all, thank you very much for the workshop and the event. Sorry we couldn't participate physically. By the way, we are committed to present virtually, which is part of the world nowadays. So it is become somehow make the life more easier. Actually, the presentation Meysam will present one of our recent research regarding to detecting the intermittent earth fault and distinguishing between the intermittent earth fault and the earth fault. A little bit, our research is a little bit different with the previous presentation. Actually, in the previous presentation, the data set, they try mostly to remove the noises from the data set, which they call it as an outlier. But here we are looking for the noises in our data set to detect any kind of the intermittent earth fault. And to distinguish this kind of the fault from the earth fault. So I think the rest of the presentation, Meysam will take over and he will present about our recent research in this topic.
Hello, everyone. I hope you are all doing well. My name is Meysam Pashaei. I'm working as a project researcher at the University of Vasa since about 6 months ago. And from next semester, I will pursue my PhD at this university as well. I have tried to remove some slides in the beginning because they were mostly about definition, about artificial intelligence and deep learning and so on. So I would like to start about two simple samples in power system. This is about, let's turn the laser point. Okay, it seems that it doesn't. Let's see.
Just try to.
Okay, and this is option. Okay, thank you. It is a simple example from 230 kilovolt simple power system in which we have substation number 1 and substation number 2. In this simple power system, we have an earth fault, which is a connection of one of the phases into ground, and this connection is a permanent connection, which is known as earth fault. Since we have digital relays in this substation, and so we can detect current and voltage, and based on a simple equation, I mean dividing EA by IA, we can calculate impedance of the system, and the impedance trajectory in distance relays is like this, which shows that this earth fault is occurred in the first zone of power system. So in this situation, since we have a precise equation for a power system, there is no need to use artificial intelligence or machine learning techniques. But what if we have a fault with high impedance, with different impedance ranging from, for example, 1 ohm, 2 ohm, 100 ohm, and even in the range of kilo ohm? In this situation, the problem will arise, and maybe there is a fault in the first zone, and because of that high impedance, maybe relay see it in second or third zone, and maybe the relay is unable to detect such fault. So in this situation, we may think of other solution, but again, artificial intelligence is not our first priority, because there are other solutions. And thanks to digital relays installed in a substation, we can use zero sequence current to detect and locate such fault in the network. So all in all, it's a good idea to pay careful attention to the fact that if there is some mathematical solution in this regard, then they have the first priority, but because they are so exact that we can rely on them in any circumstances. But what if the impedance is too high? In this situation, we may think of artificial intelligence or ML-based technique. Another example is about energizing a transformer in a substation. And since we want to energize this transformer, we have a current which is by far more than nominal one. I mean, maybe it is 10 times more than nominal current. Since we have a differential relay in the substation, we should block this inrush current. And the behavior of inrush current, again, in this situation is above x-axis, which means we have even harmonic, I mean second harmonic, fourth harmonic, and we can make use of such harmonic to block differential relay in this situation. So most of the time in power system, especially in power system protection, we have a mathematical solution that are so exact that we use them, and there is no need to machine learning and techniques. But what if we have an intermittent earth fault whose behavior is presented in this picture? As you can see, we have a current here and we have a time here, and the duration of such fault is smaller than that of earth fault or other types of fault. And since protection relays are using mathematical solutions such as, for example, about ABB, Siemens, Cell, and other manufacturers, more than 90% of the time, and they are using Fourier algorithm or least square method to do so. So they are not capable of detecting such fault, because they need at least one cycle in Fourier, I mean 20 milliseconds, and their duration is not, for example, 20 milliseconds, or for half cycle Fourier and 10 milliseconds. So we may think of other solution. However, some researchers are searching about a mathematical solution. Maybe they wouldn't be that accurate, and machine learning techniques will be helpful in this situation. So in this study, we have recently started conducting research in this regard, and intermittent earth fault is intermittent connection of conductors to the ground, and it is common in underground cabling. And the main reason why we have intermittent earth fault can be poor insulation and loose connection, moisture, and destructive tests. And in industry, for example, in a refinery, we may have 1,000 induction motors, and only maybe about 10 MV motors, and chemical and process engineers know that how important these motors are. So detecting and locating earth fault and intermittent earth fault for the cable can be of paramount importance, because if we lose the feeding of these motors, in fact, we are losing another 1,000 motors in the industry, and it can put the whole system on the line. Another thing, as I mentioned here, is a loose connection, and maybe in the terminal of a motor, which is shown here, especially in commissioning part, commissioning engineers tend to not to tighten this, because they are always opening, closing, and most of the time, even in the beginning of a project, it can be problematic. So it's a good idea to pay serious heed to such a thing to avoid an otherwise green future in terms of earth fault or intermittent earth fault. And another reason is destructive test. For cable, we have two different tests. One of them is a Megger test, which is used for being sure about continuity, and it is most of the time for example, 30 seconds, 1 minute, and for a high-level cable, maybe more than that. And we have also a HiPod test, which is about being sure about insulation, and about MV cable. Most of the time, they are about 15 minutes or 30 minutes, and we injecting maybe 2.5 nominal voltage, and to be sure about the insulation. However, they are destructive, and they may cause intermittent earth fault. And since this type of earth fault can evolve from intermittent one to a permanent one, and for example, if we could predict this one, it can be a good idea, and it can lead to the benefits of distribution system operator to ensure continuity of service. So since we have started this study recently, I mean about 3 months ago, we had literature review, and some of them proposed using protection relays. And since they are using lower sampling rate, and they are incapable of predicting such earth fault. However, in rare cases, we have a sinusoidal intermittent earth fault, and just in this case, relays are effective. Another idea is using a special fault and disturbance recorder, and since they need a higher sampling rate, which in turn results in a higher cost, and it's not cost effective to use such methods, especially in MV or LV systems. And next one is using other methods such as traveling waves. Again, they are not cost effective, and they are just used in high voltage. I mean, maybe for 400 kilovolt, and there are some relays known as cell relays for this purpose. And the last one, which become handy in this situation, can be machine learning techniques. So if we want to summarize why we should use machine learning techniques, we can mention that in the future we will have lots of renewable energies to alleviate the situation, and to have a future proof power system, and to reduce carbon footprint. And since we have such resources, we have non-linearities, we have other issues such as cyber security as a result of digitalization, and maybe it's a good idea to use machine learning techniques in this situation. Another reason was the fact that protection relays are no longer effective to detect such fault, high impedance fault, and the fact that sinusoidal intermittent earth fault are rare can be another reasons. To study this phenomenon, we are studying a real network in Finland known as Sundom Smart Grid, which is 110 to 20 kilovolt, and we are capturing real data in this network, but we didn't use this data up to now, because as I mentioned, we have just started 3 months ago to study intermittent earth fault, but we are considering lots of scenarios, different faults in different locations, and we also modeled this network in PSCAD software. In this part, we modeled both intermittent and earth fault, which is shown clearly here. For earth fault, which is a permanent one, we have this path, and for intermittent one, which is intermittent connection of a conductor to the earth, we modeled a random signal to make the circuit breaker on and off to model this one. But in the future, we will use real data to be sure about the exact pattern. As well as this, we are using different resistor because of semi-sporadic and unpredictable nature of such fault to be exact in this situation. Next one is the idea of using fault in different time, using different cable lengths, using fault different fault duration. For example, 10 millisecond, 20 millisecond for just the earth fault. However, intermittent one is by far less than this. And for resistance for earth fault, we are just using 0, 120 ohm, but for intermittent fault, it is different. The features that we are using here is voltage and current, zero sequence of voltage, zero sequence of current, and voltage and current angles. However, we can use other features such as residual currents, whose behavior is same as intermittent earth fault. And the full chart that we want to study more is this one. First, we have data pre-processing and min-max scaling, as it is described in previous presentation. And about data pre-processing, we have filling missing data, data integration, data reduction, resolving outliers, which will be arduous task in our case, and resolving inconsistencies, which is having the same data for different methods that we are using. Another important thing is using normalization. For example, if we have a data in the range of 2000 and 6000, it's a good idea to have it in this range, because if we have both these data and this one, they have dominance over this data, and they may result in false prediction. And the formula for normalization is this one. It is the value that the normalized value. This one is the value that we want to normalize it, and in this case, it is this value. And if we use this formula, we have a normalized value, which is for this one. After data processing and min-max scaling, we want to use Gaussian and naive-Bayes K nearest neighbor algorithm with 5 neighbors, multi-layer perceptron and decision tree. And after training, we will use voting among these classifiers, and we can use another classifiers as well. And for the validation, we want to use F1 and precision, recall, and accuracy. And at the end, we will have charting and comparison and analyzing data. Another thing which is worth mentioning is parameter selection. For example, for K nearest neighbor, if we use K equals to 1, if we have new data for K1, we can see that it belongs to a triangle class. For K equals to 3, it again belongs to triangle class. However, if we choose K9, it belongs to this class, and it's of paramount importance to pay careful attention to such a thing. As well as this, if we choose a smaller value for K, it make our decision and boundaries complex, which means being sensitive to noisy data. And about higher value, we will have simple decision boundaries. In fact, it's a good idea to choose a value that when we want to test, for example, testing data, they are more accurate than training one, and it can be a good idea to use this one. And in our case, it is 5. Another important issue is using distance and the parameter for distance. For example, for Minkowski distance, if we use x equal to 1, we have a Manhattan distance, and if we choose x equals to 2, we will have a Euclidean one, and if we choose one of them, and the result would be different than each other. So we should study such a thing further to realize the effect. To validate the results, we use accuracy and precision, recall, and F1 score. However, and there are lots of criteria to do so. And based on confusion matrix, in our case, we have two groups. First one is positive, and second one is negative. This is intermittent earth fault, and this is earth fault. For example, if in reality we have intermittent earth fault and our model predict intermittent earth fault, it is true positive. And if in reality we have intermittent earth fault and our model predict earth fault, then it is false negatives. About earth fault, we have earth fault in reality, and our model predict intermittent one, it is false positive, and for true negative, it is in reality earth fault, and our model predict earth fault. So based on this confusion matrix, we will have this criteria to assess the model and the flowchart that we are presented. Based on the initial results in our research group, we are witnessing that voting classifier can be a little bit better than using these methods individually. And if we see the result in some situation, for example, in terms of recall, it is in same as in GNB1, but generally speaking, it is a little bit better than using this method, and it can reduce the risk of prediction. And these are the diagram for this criteria. One question here can be this criteria. Maybe you may ask, these criteria are the same, and is it a good idea to use just one of them? The answer is not, because in some situation, not in our case, but sometimes, for example, here we have unbalanced data. If we calculate accuracy, maybe we mistakenly think that our model is one of the best models, but in reality, it is not, because of the lower value for recall, and it can be extended to other issues as well. This is the whole that we have studied in these 3 months, and I hope in the future we will learn more during the TARTIS project and project that we have, and we apply them into our method and in our research group. And from now on, I want to talk about future studies of intermittent earth fault in our research group. I can mention that these days, due largely to widespread use of renewable energies, which in turn result in complexity in the network, and protection relays are no longer effective. However, in reality, there is no ML-based functionality in power system protection, and they are just in load forecasting and such applications. And another thing that I can mention is digitalization, and because of moving toward digitalized network, we will have other issues. For example, we will have cyber securities, and maybe we can reap the benefits of machine learning techniques in this regard. And Last one is cost, which is of paramount importance. And these days, power systems are operating closer to their thermal limits. And so we have to use communication links such as fiber optic for control and other purpose. And in this case, you are witnessing 5G. And because of state estimation, we will have lots of PMUs. And by phasor and data on concentrator, we will send the data through different mediums such as fiber optic and maybe 5G and 6G in the future into edge and cloud. And at the edge, we will do some functionalities that are time critical. And in cloud, we will have some monitoring purposes, and we can use artificial intelligence. And what we are doing in our Freezy lab, we have SSC 600, which is latest technology of ABB, which is a centralized protection device. And this device cover up to 13 feeder, up to 13 feeder that are going to secondary substations. And the idea behind this scheme is sending a different value of voltage and current through 5G or fiber optic to a centralized place. And since in this device, which is the only device that has intermittent earth fault functionality to my knowledge, we can use intermittent earth fault in parallel with machine learning and techniques to validate that method and examine this one. And so we are studying such a thing. And to do so, we have this equipment, and we have time synchronization for time critical activities. We have Typhoon Hill and Opal RT to run real-time simulation. We will have different digital relays, and we have modeled that network that I shown to you in MATLAB. We sent the analog input to the Opal RT and Typhoon Hill, and we amplify them with Omicron amplifier, and then send the sampled value based on IEC 61850 to our centralized device, SSC 600. In this stage, we modeled a merging unit inside MATLAB, but in the future, we will use a merging unit to digitalize or for sampling the values and then send to this device. And since we have all the data concentrated in just this device, we can apply machine learning techniques as well. And this is the whole about our presentation. And in summary, I can say that we have studied power system analysis in two cases. One of them was distance protection, and another one was using differential protection. And since there was no need to use machine learning techniques, mathematical solution were the best one. Next one was intermittent earth fault, and since mathematical solution have some inaccuracies, we are trying to study this one further to see they are effective or not. And we also mentioned the main reasons why machine learning techniques are a good idea to be used in power system. However, up to now, we don't have any functionalities in terms of power system protection. We also talked about the importance of data and pre-processing and voting and classification to reduce the risk. And the last but not least was using a centralized device to study this further. Yeah, this is the whole about what we have conducted up to here. Thank you for your time and consideration. And you can see some of the reference here. And one of the interesting papers which is presented in CIRET conference is about SSC 600 devices and other interesting papers. If you have any questions, feel free to ask. You can also ask your question via email, and you can get back to us whenever you wish. Again, thank you so much for your attention.